Multinomial distribution. So suppose there are n objects. Now in binomial, you have two kinds of objects. So the way we described it was that there are n trials and every trial has two possible outcomes. It could also be described as n objects and they contain two types of objects. So what if we have more than two possible outcomes? We can still handle those. And if, for example, you have three possible outcomes for every trial, then it's trinomial distribution. And similarly, you could have any number of possible outcomes. So in general, if there are more than two possible outcomes, then we refer to the distribution as a multinomial distribution. And we're assuming that the other conditions of the binomial distribution are still holding, that the events are independent, the trials are independent, and the probability of success or the probability of each outcome is the same in every trial. Let's open up the binomial conditions, if I can. So yeah. So the first condition is the same in multinomial, that it involves, not if involves, but it involves performing n trials of an experiment. Trials are independent. These two are exactly the same over here as well. And then here, instead of two possible outcomes, you have more than two possible outcomes. And the probability of each outcome is the same in every trial. That's how it would be replaced. And so the formula for multinomial would be f of x1, x2, x3, and so on would be n factorial divided by x1 factorial, x2 factorial, x3 factorial, and so on. And then p1 power x1, p2 power x2, and so on. So where n is equal to total number of objects, okay. Let's say objects are of type 1, 2, 3, and so on. X, so P1 is the probability that object is of type 1. P2 is the probability that object is of type 2, and so on. P3, probability of type 3. So x1 is equal to number of objects of type 1 x2, number of objects of type 2, and so on. So in this case, we have three kinds of offsprings: red, black, and white. According to their genetics theory, a certain cross of guinea pigs will result in red, black, and white offsprings in the ratio 8:5:4. Find the probability that among the 10 offspring, 4 will be red, 3 would be black, and 3 will be white. So over here, we will have let's say probability of red would be 8. So they go red, black, and white are in this ratio 8:5:4. So the red probability would be 8/8 plus 5 plus 4 is equal to 8/17. Similarly, white probability. The second one is black. Black would be 5/17, and white would be 4/17. And so we need the probability that we have 4 red, 3 black, 3 white. So 4 red, 3 black, 3 white. So look at the formula. N in this case is 10. Formula is n factorial divided by all these x factorials. So n factorial would mean 10 factorial. And we'll have 4 factorial, 3 factorial, 3 factorial. And then we have, after that, p1 power x1, p2 power x2, and so on. And so p1 is like pr. So 8/17 power 4. Then black probability is 5/17, and we have 3 blacks. And then white probability is 4/17. And we have 3 whites. So let's multiply all this out. So 10 factorial. Okay. And divided by 4 factorial is 24, and 3 factorial is 6, and 6. Okay. And 9 times 8/17 power 4 times times 5/17 power 3 times 4/17 power 3 so 0.0683. So this one is also multinomial. So let's open a new file. The probabilities are 0.4, 0.2, 0.32, and 0.08 respectively that a delegate to a certain convention arrived by air, bus, automobile, or train. What's the probability that among the 9 delegates, we have 3 arrived by air, 2 by bus, so probability 3 air, 2 bus, 2 auto, and 2 train. Well, that would be equal to the n factorial, and n in this case is 9, and 9 of them. Okay, and then we have these factorials, 3 factorial, 2 factorial, 2 factorial, 2 factorial. And probability is 0.4 for the heirs, so 0.4 power x for the heirs, 0.4 power 3, 0.2 power 2, 0.32 power 2, and 0.08 power 2. So let's figure this out. 9 factorial on the top. Okay, divided by 3 factorial is 6, and 2 is 8, so divide by 48. Okay, and then times 0.4 cube times 0.2 square times 0.32 square times 0.08 square. So 0.0127.